What else I want to talk to you about? Okay. I know that at least for some of you, you're starting to feel that the material has gotten out of your hands and you're lost, right? Now, this is not your fault, and honestly, I can say it's not our fault as well, because in every class of statistics I've taught so far, this happens. Okay, this is the stage that this happens when we're getting near the end of two-way ANOVA. Like the first lesson were okay, and then one-way ANOVA was okay, and then okay, plan comparisons was okay, but then two-way ANOVA, just things start to break down. So part of what I'm going to do today is going to repeat stuff that we've already said. Okay, we want to rescrew some of the screws, some of the explanations that we already talked about. My professor in university likes to say that these lessons have nothing new in them. We already talked about everything that is in this lesson. Okay, so I can't say that's absolutely true, but a lot of the material is repetition and just reinterpretation of the same things we've already said. Okay, so today we're going to calculate interactions and simple effects. That's the main thing. We talked about two-way ANOVA. We talked about it in the descriptive level, right? We looked at the averages, and then we understood what's going on. We said, is there an interaction? Is there not an interaction from a descriptive point of view? But because this is not a descriptive course, this is an inferential statistics course. We have to look at the descriptive statistics and say something that we can infer about the population. Okay, that's the magic that we're doing here. We're looking at a sample and we're trying to infer about the population. So today we're going to talk about inferential statistics. Okay. Today's story is about Nietzsche, a personal favorite of mine, very misunderstood philosopher. Talked a lot about how to live a passionate life, to live large, and how to be committed to your own life, live in the moment. So this is about the meaning of life. So Nietzsche was interested in what makes a person's life meaningful. He was interested in one variable in particular, a person's passion in life, for life. He sampled 20 participants and divided them into two groups according to how passionate they are. Never mind how he measured passion, never mind how he measured meaning in life, just accept that that's what he did, okay? So, this is the design, just two groups. Of course, we're always starting with one-way ANOVA and building up to two-way ANOVA. So this is what we have. We have two groups, low passion group and a high passion group. Okay. And for each group, we have different individuals, right? We have this individual, the meaning of life is 4, and this is 5, okay? So different people, different values, right? The dependent variable is the meaning of life, right? Meaning in life, and passion is the independent variable. And we're looking at the averages, right? We have average of the low passion group and average for the high passion group, and we can see there's a difference. There's a descriptive effect, right? There's a descriptive effect of passion. But this is not enough. We need to ask, is this descriptive effect significant? If it is significant, we can say with some degree of certainty that this difference was not caused by chance. Right? There's a real difference between low and high passion. If it's not significant, we can't say that with certainty. Instead, we'll say, okay, there is a descriptive difference, but we can infer about a real difference in the population. Right? So this is the method we're using. We're looking at the averages and we're trying to say, okay, is this difference a real one or not a real one? So, first up will be to calculate the variance between the groups, right? SSB is the sum of squared deviations between the groups. It's a measure of variance between the groups. So how do we do that? We have 10 participants in each column, right? So 10 participants times 5, the average of low passion, minus 6. 6 is the grand mean, right? The total mean. So 5 minus 6 squared times 10 plus 7 minus 6 squared times 10. Okay? So this is our measure of variance between the groups. The larger the SSB, the larger the estimate of variance, right? The more impressive the result. So we have SSB, and now we have to think about SSW. If we have SSB variance between the groups, we also have variance within the groups. The variance within the groups, I remind you, we called unexplained variance, right? Unexplained variance, because we don't know why do we have that variance. Look at this column, for example, okay? This participant has 2, and this participant has 7. Why? We don't know. Because people are different, because one of them woke up grumpy that morning. We don't know. Okay? So because we don't know, we're going to use this estimate of variance within the groups as our estimate of error. Okay? Not an actual error. The fact that these two are different is not a mistake. Okay? But we're going to use it as our estimate of error because we want our effect, this thing, not to be a product of just random chance. Okay? So this is used as error by us, the researchers. Okay, so SSW variance within the group. Okay, so I remind you that SSW is simply calculate the sum of squares for group 1, and then calculate the sum of squares for group 2, and then add them up, right? So SS, sum of squares for group 1, is this. SS1 is 4 minus 5 squared, right? First participant minus the group average squared. And 6 minus 5 squared, and 5 minus 5, and 2, and 5, and 7, and 4, and 5, and 5, and 7. So we go one by one, and we actually calculate the variance within that group. Okay? All remember? This seems right, clear by now? Second group, same thing. Right? We look at the variance within that group as well. We calculated SS1 and SS2. We can calculate SSW as the sum of both. Simply enough. Okay? This is really variance within the groups. Once we calculated SSB and SSW, we can draw this table, the ANOVA table, okay? And simply plug in all the different components. SS, degrees of freedom. Okay? So degrees of freedom, you have it in the formula sheet. For the groups, it's K minus 1, right? Number of groups minus 1. And for the within is the number of participants minus the number of groups. Okay? So N minus K in this case will be 18. You have your degrees of freedom. You can calculate the MS, right? The mean sum of square between, mean sum of square within. And then from that you can calculate F, right? This is the ratio that we care about, variance between divided by variance within. By how much the variance between overcame the variance within. By how much our effect overcame chance. Okay? If we have a large F ratio, we're pretty convinced, okay, this is an actual result. If we have a small F ratio, let's say F equals 1, okay? This means that our effect, we cannot ascribe a real, we cannot say it's a real effect, okay? Because it did not overcome chance. So in this case, our F is 3.75, and we have the final stop, compare it to a critical F, and then we get this result. F is smaller than the critical F, meaning that Nietzsche cannot say, at this point, he cannot say that passion significantly affects meaning in life. Okay. He just can't say it. He can't conclude it. We can see this descriptive difference, but he can't conclude that this is an actual effect. He cannot publish an article saying that, look, passion is a really important thing in life. Okay. Any questions so far about this reminder? So SSB, SSW, MSB, MSWF, all clear to you? Great. So now, of course, we add another variable. Okay? Nietzsche was well known for his philosophy, but also for his mustache. In German, also Mustache. So, undiscouraged by the results, Nietzsche noticed that exactly half of the subjects had a mustache. Okay? So half have a mustache and half don't have a mustache. This is actually Nietzsche without a mustache. He said at some point that, why do you grow such a mustache? Because I don't want people to see me. When they meet me, all they see is the mustache. They don't see the me behind the mustache. So it was used as a disguise of a sort. So we add the variable of a mustache. First of all, here's a sentence. You need cows in your life to give birth to a mustache. That's not the real phrase. You need cows in your life to give birth to a dancing star. So we said passion, right? So Nietzsche believed that there's a chaos in the soul that could give birth to creativity and brilliance and stuff. Okay, so mustache and no mustache. He adds the second variable to the design. How will this change things? Okay, so open question. I'm going to answer it, of course. Okay, but the first stop I want to ask, that we're going to go through, is what will happen to the effect of passion, right? This same effect of passion, of course, the averages stay the same, right? You understand why this average is still 5, right? Because it's still the average of this entire column. And this remains 7, because this is the average of the entire column. It doesn't change anything that we split the groups in half. Okay? The average, overall average of low passion and high passion stays the same. So let's see what happens to the first effect, the effect of passion. So now we have this, and it's color-coded, so when you go over the material again, you can see it very clearly. So we have specific averages, right? X1, 2, 3, and 4. 4 groups now, right? But the overall averages, X bar low, X bar high, are the same. This means that SSB for passion remains absolutely the same. There is no change. Sum of square between groups for the passion variable remains the same. Okay? Now here's a common mistake that students make. Not really a mistake, something that confuses a lot of students. What students do is look at data and then try to find the terminologies. Right? We talked about a main effect. Right? And people look at the data and say, okay, where's the main effect? And that confuses people because we don't really remember what a main effect means, not exactly. And trying to find that terminology in the table is doing it the other way around. What I want you to do is, first of all, try to understand what the data tells you before you try to describe it by a specific terminology. Okay? So what do we see? Do we see that the overall average for low passion is lower than the overall average of high passion? Yes, because that's exactly what we saw before. The overall average of low passion is different, lower than the overall average of high passion. Okay? Now that I said this out loud, I will ascribe the name main effect, right? I won't try to find the main effect and then look here. I'll try to describe the data and then say, oh, overall average and overall average, that reminds me of a main effect. Okay? That's what I want you to do. Don't try to go from the other way around because that's confusing. Okay, so this remains the same, SSB remains the same. Dividing each group to 2 does not change the marginal means and therefore does not change SSB. Okay? So this is pretty easy. But what happens to SSW? This was supposed to go in one by one. Imagine it goes in one by one. So SSW changes. How does it change? Because now we don't have only 2 groups to look within. We have 4 groups to look within. Now, an intuition will be to say, okay, SSW will increase because we have more groups. But that's wrong. Okay? That's not the right answer.
Why?
Now, let's look at it. Okay, so look at this, for example. Let's see. Let me give you this example. Okay, so let's look at this person. Okay? The difference between this person and the previous group, okay, high, is 9 minus 7. Okay? This difference is larger than this difference. Right? Once we look at the group average, when the group is tighter together, the variance within the group becomes smaller. Okay, let's look at another example. This person, right? Value of 1. The difference between 1 and 5.4 is a smaller difference than 1 minus 7. So actually, when we add more groups, we have a potential of reducing the within group variance, right? Because the average now is a better representative of that group. Yes?
It seems that the more, so SSW is the unexplained variance. Yeah,
Yeah.
it's like what we can't explain.
Right.
About. And so it seems like the more reasons we have why you can be happy in life, the more we can explain.
Exactly so. Look, we're in sciences, empirical sciences, we have a deterministic point of view about life. We have a feeling that if we simply measure enough variables, we'll understand everything, right? So if I measure all the variables in the world, each cell is supposed to have no variance within it, other than, for example, like the measurement tool. Okay. So the more things that you use to explain the variance, the less unexplained variance you'll have. So now, instead of looking at SS1 plus SS2, the process is just a little bit longer. Okay. So we have SS1. SS1, we look at group number 1, low passion with a mustache, okay? And then look at 4 minus 4.4, 6 minus 4.4, 5, 2, 5. Finish with group 1, move on to group 2. 7, 5.6, 4, 5, 5, 7. Third group, fourth group, okay? It's the same process, only now you have more groups to look at. SS1 plus SS2 plus SS3 plus SS4 equals 66.8. Now I forgot to write down, I want to write down in advance what was SSW before. SSW before was 96. SSW now is 66.8. Okay. SSW got smaller. Okay. Why did it get smaller? You have 2 reasons which are both one and the same. One thing is that the group average is a better representative, so you have less differences within each group. The reason, this is the mathematical reason. The reason this happens is because what we said, we explained more variance. Okay? We explained more variance. So this is what happens. We have the one-way ANOVA, okay, and we had SSB and SSW. And we have the two-way ANOVA. And in the two-way ANOVA, we have SSB1. Of course, it's absolutely the same as SSB in the one-way ANOVA. Okay, SSB remains the same. But you also have SSB2. And you also have SSB interaction. Okay? We didn't calculate it yet. But the reason why this is smaller is because you added something to the pot. You explained something. You explain something, you reduce the unexplained variance. So this is variance only explained by the main effect. This is variance explained by two main effects and an interaction effect. So the more explained variance, the less unexplained variance. Okay, I want to hear questions about how we calculated SSW in the two-way ANOVA, and I want to hear questions about explained variance, unexplained variance. Is it clear? Crystal clear? So, if I ask you in the test, a researcher changes design from one-way ANOVA to two-way ANOVA. He found the second main effect was significant. What will necessarily happen to SSW? Smaller. Right? Because if it's a significant, of course it explains something, right?
And if it would be not significant, also smaller. It's always smaller.
If it's zero, if it explained absolutely no variance, SSW remains the same.
But even if there's any effect.
Right.
Effect,
Any effect, SSW becomes small. Absolutely. If it's significant, of course, it explains
You
something.
can have a non-significant
Right,
effect.
right.
The fact that there is an effect makes it small.
Yeah. Any descriptive effect.
If it's not significant, you would still refer to it as the SW.
SSW becomes smaller the moment you have any descriptive effect.
Okay.
Any descriptive
Mathematically, it gets smaller, but
Yeah.
we wouldn't deal with it as.
SSW becomes smaller. SSW is a mathematical component. Okay. So we know what's SSB. SSB remains the same. We know what's SSW. Let's look at the effect of passion again. So SSW. Okay. Sorry. This again is supposed to go one by one. It didn't. So let's look at it like this. SSW is our estimate of what is considered chance. The more groups, the better, and smaller the estimate. Okay? The more groups, the more things we explain, the better the estimate. SSB1 was 20, so MSB is 20. SSW is 66.8. MSW, notice, it's not 18 degrees of freedom as we had before. Right? Before we had N20 minus K2 was 18. Now we have N20 minus K4, right? We have 4 groups now. So the degrees of freedom is 16. Nevertheless, F is now 4.79. 4.79, which is larger than the critical F, okay? The effect of passion, which was before non-significant, now is significant. The effect of passion was not significant in one-way ANOVA, but the main effect of passion is significant in two-way ANOVA. Why did that happen? Because the unexplained variance became smaller. Our estimate of chance became smaller. Now you might think that's unfair. Why do we enjoy from a smaller estimate of chance? The reason why is because it became more accurate. It became more accurate, okay? The reason it became smaller is because now we have a better understanding of what is this estimate. Okay? So if the estimate of variance that we had before is exactly right, there's no difference, it's supposed to stay the same. It became smaller because we understand better what we consider chance is now small. So the power of the design increased, right? F was not significant before. F is significant now. Okay, so the power of the design increased. What does that mean? Power means the likelihood to reject the null hypothesis. If we have a smaller estimate of error, of chance, we have a larger likelihood to reject the null hypothesis. If we have a smaller estimate of chance, we have a higher likelihood to reject the null hypothesis. And if that doesn't ring a bell, you should go back, way back to lesson 2, okay? Remember about power. Power simply means that it's better for us, okay? More power means it's easier for us as researchers.
Power is a small estimated chance.
The smaller the estimated
So that's
chance,
power?
the more power we have
Okay.
in the design. Okay, but notice the power increases only when the new variable is relevant. Okay? Only when the new variable is relevant. If I'm adding, instead of mustache, which for some reason is very important in Nietzsche's design, instead of mustache, I'll add something like hair length. Okay, let's say hair length is absolutely not relevant to the meaning of life. Now I add hair length, short versus long. It doesn't explain anything at all. Then not only do you not increase the power, you actually decrease the power. So you only add relevant variables. How do you know? You don't know. But you want to add only relevant variables. Yes.
Does that mean that it has to be like significant?
No.
Like, is it
No.
a descriptive difference that like this might be by chance? Like let's say it's like 0.01 difference descriptively.
So
One
that
is like 0.01 bigger, so then it would still increase your power.
you have a good intuition that there's a gray area that we don't know. Okay. I can tell you that for certainty, if it's a significant effect, you most definitely increase your power. Okay? Because you explained a lot of variance. Enough variance for have a significant effect, you increase your power definitely. There is a gray area where you can have a very small descriptive effect and you still might decrease your power. In the terminology of this course, if we say that the effect, the new variable is irrelevant, it means you decreased your power.
Irrelevant means not
Just
significant.
nothing.
Not significant.
Nothing. Nothing.
So not,
When we say irrelevant, it didn't explain anything. No SSB due to the new
anything
one.
more than 0, then
Yes. That's the level we're going to ask you about. Okay? So a question in the test, a researcher added a variable, let's say hair length to the one-way ANOVA, and he found that hair length did not contribute anything to the explained variance. What happened to the power of the design? The power became smaller.
And it becomes smaller.
Yes, because it was completely irrelevant. Okay? If the variable is completely irrelevant, meaning it did not explain any variance, okay, it means that the power of the design became small.
Why doesn't it
because
just
of the
stay the
degrees of
same?
freedom.
Yes, basically yes. Yes.
So relevant doesn't necessarily mean main effects. Is that what you're saying?
Yes, we're not going to talk about. We're not going to try to catch you in this corner, right? We're not going to trick you. So I'm saying is we're going to talk about it very broadly. Okay, either it was significant, so it increased the power. Significant, like a significant effect.
Yeah.
It necessarily increased the power, or it was nothing, and then it didn't necessarily decreased the power. Okay, we're going to talk about it in a very, very polarized way. It's not true to talk about it in a very polarized way. There is a scale here. Okay, there's a balancing point, but we're not going to ask you about the balancing point. Okay, so yes.
Why exactly does it decrease power?
Because of degrees of freedom. Okay, so look at this, right? MSW is SSW divided by n minus k. If SSW remains the same, but the degrees of freedom decrease, then MSW increase, then F decrease, everything becomes worse. Okay? Basically because of the degrees of freedom. Okay, you don't have to know that. Okay. Let's continue. So we found a significant main effect. Now, what would have happened if we had found a significant main effect with 3 levels? Okay, let's say this is our design, a 3x2 design, A has 3 levels. If A has 3 levels and we have a main effect, it means that there is some difference between the levels of A. Okay? Right? Remember, when we have 3 groups, we don't have a one-sided hypothesis. We can't conclude about what exactly is the difference. We just say the vague sentence, there is some difference between the groups. Okay. So whenever we have a main effect with 3 levels, we have to conduct post hoc tests. Remember? I think it was lesson 5 or 6. Post hoc test. Whenever we don't understand something, we have to conduct more tests. Okay, so in this case, we have A1, 2, and 3. Perhaps the main effect was caused because A1 was different from A2, but not from A3. Right? This is a larger difference. 10 and 5 is a larger difference than 10 and 7. Maybe it's because A1 was different both from A2 and from A3. Okay? So whenever we have a main effect with 3 levels, we have to conduct post hoc tests. Yes?
Is this a post hoc test on 6 groups? Is that
No,
what
just the
it is?
3 levels.
Just, but you don't take any
No.
other. Okay.
Main effect. Absolutely like a main effect. Now, this is something that is going to be taught in the recitations, but not here, so it's not going to be in the quiz, okay? How exactly to conduct the post hoc test? How to calculate the post hoc test, okay? So that's going to be in the recitation, but not in the quiz, okay? Just the main thing you need to know for this point is that if you have 3 levels, you have to conduct, and if you have a significant effect, of course. Okay? Significant effect with 3 levels, you have to conduct. Okay, so that was the main effect. Of course, we can talk about the other main effect, right? We added the variable of the mustache. So we can talk about, is there a main effect for the mustache? And again, I'm doing this the exact same thing I don't want you to do. Okay, I'm saying let's look at the other main effect. Forget about the terminology. Okay, let's look at this table. Can you say that people with a mustache, overall, regardless of high passion or low passion, right? People with a mustache, do they have a different meaning in life than people without a mustache? Yes, right? We even highlighted which averages you're supposed to look at, right? So this is the mean for mustache in general, and this is the mean for no mustache in general. Now you can apply terminology. So this is not just the means for mustache and no mustache. These are the marginal means. Okay? And if you have a difference in the marginal means, which means you have not just an effect of a mustache, you have a main effect of a mustache. Okay? Look at the data first and then try to apply the meaning. So you have this. The method is absolutely the same. Okay, you have SSB2 equals 10, why 10? Because you have 10 people with a mustache. 10 times this minus this, and 10 times this minus this. You get SSB2 equals 5, and then you calculate MSB2, and then you calculate F. F equals MSB2 divided by MSW. Which MSW is that? The same MSW we calculated a few moments ago. Same MSW for all the effects, right? The reason why it's the same MSW is because it's the most accurate MSW that we have, right? We calculated MSW by using more groups. We're always going to use the most accurate MSW that we have, okay? So the same MSW for all the effects. And then you get this, and you see that it's a really small f. F equals 1.19. It's probably not significant, f equals 1.19 is smaller than, look, the same critical f. Okay. So we don't have a significant main effect for the mustache. We can say that overall, regardless of passion in life, mustache has an effect on meaning in life. Okay, so basically it's the same thing, right? We can look at it from that way, it's the same method. The last stop will be the interaction. This is the hard nut to crack, okay? So this is something that you've already seen in the presentations. We're going to repeat over it, and then I'm going to add something, okay? So add something theoretical to the mix. Now let's, at the first stop, look at the interaction from a descriptive point of view. From a descriptive point of view, let's say Nietzsche says that the effect of passion in life is larger for people who have a mustache than people who don't have a mustache. Right? Listen to the phrasing. The effect of passion, low versus high, is larger if you have a mustache than if you don't have a mustache. So let's see. We're looking at low passion versus high passion. For people with a mustache, it's 4.2. Okay? People without a mustache, minus 0.2. Okay? Not only do we not have not only is the simple effect smaller, it's actually in the other direction. Okay? Passion seems to be worse for people without a mustache. Now, again, you can look at the data, understand what's going on, and then apply the terminology, okay? Because if I'm telling you, is for people with a mustache, do we have a positive or a negative effect of passion? So you can look at 8.6 and 4.4 and say, okay, this is a positive effect. And for people without a mustache, do we have a positive or a negative effect? You can look at this, 5.4, 5.6, okay, there's a negative effect. You can understand all of this just by looking at the data. And then you apply the terminology. This is a simple effect of passion, right? Because we're looking at low passion versus high passion, among the mustache group. So simple effect of passion among the mustache group and simple effect of passion among the no mustache group. And we're asking, is this simple effect different from this simple effect? Okay. How do we look at that? We can subtract the two simple effects. So we can see 4.2 minus 0.2, okay? We get 4.4. Because this is not 0, we can say, okay, there's a difference between the simple effects. Descriptively, there is an interaction. Okay, all clear up until this point? Okay, so descriptively we have an interaction. Okay, but now we have to ask ourselves, is this interaction a significant interaction? Okay, a significant interaction. If it's not a significant interaction, we can't conclude there's an actual interaction in society. Okay? If we don't find a significant interaction, we have to say, look, this difference was caused by chance. Okay? We can't really speak of it. Another example, which will be more relevant to our life. So let's say you have a study of Ritalin. Okay? One group is an ADHD group, and one group is a no ADHD group, and you're giving one group Ritalin, and the other group you give no Ritalin, and Ritalin, and no Ritalin, and you want to say that Ritalin only affects people with ADHD, okay? But does not affect people without ADHD. So you have to look if the interaction is significant, right? Because if you find a significant main effect, let's say overall Ritalin improves your score in the test, okay? You find a significant main effect, but you don't find a significant interaction, you'll have to conclude that Ritalin affects everyone and not just people with ADHD. Okay, descriptive interaction. So the first method, and the method that you learned in the class, was to calculate something new, something that's called SSB overall. SSB overall. What is this new SSB? We keep saying there's more SSBs. SSB overall is simply the sum of SSB1 and SSB2 and SSB interactions. What is explained by our design? Okay? Everything that is explained by our design. Another way of looking at SSB overall, it is what is the variance between all the groups. Right? If we look at the main effect of passion, we're looking only at the variance between the two passion groups. If we look at the main effect of mustache, we're looking only at variance between the mustache groups. SSB overall will look at variance between all the groups, between this group and this group and this group and this group. So we're going to calculate SSB overall. Okay. And then from SSB overall, we're going to extract SSB interaction. Okay. Is it clear why we can extract SSB interaction? If SSB overall equals to SSB1 plus SSB2 plus SSB interaction, and we found SSB1 and we found SSB2, the only thing we need to get SSB interaction is to find SSB overall, and then SSB interaction equals to SSB overall minus the first part minus the second part. So this is a new calculation. Okay? This is the one bit of new material, right? You had basically in the recitations. This is the formula. Yes?
Is it the only way to calculate it?
No, there is another way we're going to see in another second. We're not going to use the other way, but I'm going to use it to make a point. This is the formula for SSB overall. The sum of, right, sigma is the sum of n, and you have this small index, AB. AB basically says, look at a very particular group, okay? You're not looking at a group of marginal means, you're looking at this group, right? Column A, row B. Okay. So the number of participants in this group times the average of this group minus the grand mean squared. So basically, you're just looking at all the groups, okay? And it's asking, what's the variance between all the groups? How many participants do we have in the low passion mustache group? Overall, we have 20 participants. So the low passion mustache group, we have 5 participants. Okay? Is that idea clear? So 5 participants times 4.4 minus 6 plus 5 times 5.6 minus 6. And this goes on until you finish with all the groups. Okay. And we get 49.2. Actually, I think there's miscalculation here maybe.
I don't understand what the 5 comes from, the NAV.
So 5. We basically ask how many participants are in this particular group. Okay? Now we said before we have 20 participants in our design. So in this particular group, we have 5 participants. Right? We have 5 participants here, 5 participants. Okay. So this will give us what we call SSB overall. Overall variance between all the groups. Once you have, oh, this is okay, fine. Once you have SSB overall, okay, SSB overall, you can extract SSB interaction. How do you extract it? You remove all the parts we already calculated. You remove SSB for the passion, right? It was 20. You remove SSB for the mustache, 5. We already calculated that. And you get that SSB interaction is this number, 24.2. Is this idea how to get to SSB interaction clear? I want it to be very, very clear. Yes, you have questions?
I'm having trouble phrasing my question.
Okay. Now, there's something in this method that for me feels a bit like a cop-out, right? It's weird. Why can't we just calculate SSB interaction? Why do we have to go to SSB overall and then calculate SSB interaction from there? Can we just calculate SSB interaction? Right? So we can, but the thing is, it's much more complicated, okay? This is the easier way. So we're teaching you this method because it's easier and we're not a very mathematical oriented course. But now I'm going to look at the other way just to make a point. Now I'm going to say this in advance. You don't have to know the mathematical method that I'm going to show you, okay? The other method. This is the only method you need to know, okay? But I am going to make a point, and the theoretical point I'm going to make, you do need to know. Yes, you want to ask something? Just a second. Okay.
That's the question.
Yeah.
I understand intuitively that if we don't look at the interaction, we explain less because maybe passion and mustache have nothing to do with each other.
Mm-hmm.
So when we combine them, we explain more.
Mm-hmm.
But mathematically, what changed there that gave us a higher, that gave us
More explanation.
Yeah, in the equation.
Okay. So basically, as we say on one foot, I can tell you that this difference is what changed. But maybe the next few slides will give you something a bit more elaborate than that. Okay. Now, I told you a few weeks ago that if we don't have an interaction, we call that situation additivity. Additivity is a situation where there is no interaction. And the result can be explained by the addition of the main effects, right? That's why it's additivity, because everything can be explained by adding up the main effects, okay? Now, additivity being the situation where there is no interaction is RH0. Our null hypothesis about the interaction is that there is no interaction, there is additivity. Okay. Now, I want to ask, what would such a world look like? What would a world where there's only main effects, how would it look like? So, to ask that, I need to find what is the effect of each main effect. Okay? So, this is the effect of high passion. To get the effect of high passion, I need to look at the difference between high passion and the grand mean. Okay? High passion gives me 1 point. Is it clear what am I saying here? High passion, overall, regardless of the mustache, gives you 1 point in meaning, right? Because high passion people with high passion in general have 7 points of meaning, and the grand mean is 6. The grand mean is supposed to be the average person, right? The average person has 6 points in meaning, and people with high passion have 7 points in meaning. So we can say that high passion adds 1 point. Okay? We can also say that low passion gives you minus 1 point. Right? It's the exact opposite. High passion gives you 1 point relative to the grand mean, and low passion takes away 1 point relative to the grand mean. We can also ask, what is the effect of the mustache? Same thing. Mustache minus the grand mean, half a point. No mustache minus the grand mean, minus half a point. Now these are the effects. These are the overall effects of passion and of the mustache. By looking at these, okay, +1, -1, +half, -half, I can draw what I can call the situation of additivity. How would the world look like? How the world would look like, it's supposed to be, if H0 was correct. So, mustache, low passion, okay? What would we expect? If there is no interaction, then we know that people with a mustache are supposed to have half a point more relative to who? The grand mean, the average person, right? And people with low passion are supposed to have -1 point relative to what? Relative to the grand mean. So, the average that we expect under the situation of additivity is 6, right? The grand mean, -1, right? Because of low passion, +1/2. This is what would happen if we simply add up the main effects. I need this to be clear before we continue. No, it's not clear. Okay. Going back. Is it clear why this is the effect of high passion, low passion, no mustache, no mustache? Now I want to add up these effects.
But how do you get these?
These? So what is the average of high passion? It's 7. Minus the grand mean,
Nice one. Okay.
right? So people with high passion relative to the average person have 1 more point.
Okay.
Okay?
We don't need to know these.
We need to calculate them.
Yeah. Okay.
Yes.
So why is it just the additivity? I mean, between the low passion and mustache and no mustache, that they would be equal, but between the low passion and high passion, there would be a difference. So there still would be an interaction, no?
Wait. You'll see. It won't be an interaction because we're just adding up the main effects. You'll see there's no interaction in a second. Okay. Now, what we're trying to do now is to simply add up the main effects. Okay. So, for low passion people with a mustache, we'd expect that they will be like the average person, but they will have the addition of the mustache, but the drawback of having low passion. So 6, the average person, minus the low passion effect, plus the mustache effect. So if we simply add up these effects, we get 5.5. And if we have no mustache, low passion, we have both the effect of low passion, -1, and the effect of no mustache, -0.5. And if we have high passion with a mustache, we have average person plus passion plus mustache, it's this. And if we have x4, high passion, no mustache, average person plus 1 minus 0.5 is this. Just one more second, then I'm. So is it clear how I got all these values? Okay. This is the world where there is absolutely no interaction. Now, I'm saying there's no interaction. Let's see if that's true. 7.5 minus 5.5 is 2. Oh, sorry, there's a mistake here. This is supposed to be 6.5. This is 6.5. My mistake. I'll upload the corrected presentation. So, 7.5 minus 5.5, 2. 6.5 minus 4.5, 2. Right? The simple effect of passion is the same for people with a mustache and no mustache, meaning there's no interaction. Right? Because this is the world from the point of view of additivity. This is what the world should have looked like if there is additivity. Yes, question?
No, yeah.
Because of it, yeah. Yes.
I don't know if I'm getting like bogged down just to kind of phrase something, but because we have different directions in some of the symbol effects, it sounds like it's masking. It sounds like additivity is masking like small interaction effects that could be.
So this is a very theoretical exercise we're doing because we're trying to draw up a world that doesn't exist, right? This is not the actual values. Look, there's a difference. We're trying to draw a world where there is no interaction. In that world, there's only main effects. It's not a real world. We invented it right now. Okay. Now we have a reason why we invented it. Because now what we want to see is how much do we deviate from additivity? What's an interaction? An interaction is a world where there is no additivity, but it's not black or white, right? It's not yes interaction versus no interaction. We want to know by how much do we deviate from additivity, right? When we ask about a main effect, we ask how much do the groups deviate from one another? Now we're asking by how much do we deviate from additivity? And now that we drew a world of additivity, okay, we can do this. Sum of real score minus additivity. What's the deviation from additivity? This is the real score. Sorry, this is the real score. People with a mustache and low passion. This is the world of additivity. A fake world. But we can ask, okay, what's the difference between them? 4.4 minus 5.5 squared times 5. And no mustache, low passion. The actual score was 5.6, right? But this score is 4.5. There's some deviation. There is some deviation. And then this top, high passion with the mustache, and this top, yes.
I'm sorry that I'm not really understanding why we care about the difference between the word we just made up.
So again, think about what theoretically we're doing here. We're trying to evaluate how strong is our interaction.
Okay.
An interaction phrased in this way is a deviation from additivity, right?
Right.
So we want to draw this fictional world of additivity and ask, by how much do we deviate from it?
Why do we want to know how much we deviate from that?
So think about this, Julie. Let's say we have this interaction. Okay. This is a very small interaction. In this situation, you might say, I'm not convinced that this is a real interaction. On the other hand, this seems like a real interaction. Why is this not convincing? Because the interaction is so small. What's small about it? It's a small deviation from additivity. Because the state of additivity is this. This is a very small deviation from that. Okay? But this is a very big deviation from that. So what we're actually asking when we calculate SS interaction is by how much do we deviate from additivity? Yes?
Okay, so how is this different, or is this the behind the scenes of essentially just finding the F-score? And
It's exactly behind the scenes. That's exactly the point, because what do you think will be this value? It will be exactly the value that we found before, right?
This is a different way.
It's a different way that you don't even have to use. What I want to make a point here is that interaction is a deviation from additivity. When we don't have interaction, we have additivity. Or a very slight deviation from additivity. When we have a real interaction, we'll find a significant deviation from additivity. Yes, two more, and then we'll have to continue because we have some more material to cover. Yes?
So does that mean that if we do have additivity,
This is supposed to be 0. If we absolutely have additivity, then this is supposed to look like this, and we'll have 0, no deviation from additivity. Yes?
no, but sorry, you said that additivity like is a before that it was a made up.
Yes, but if we really do have additivity, absolutely we have additivity, then the fake world that we create is an exact replica of the real world.
Right.
But
That's what I'm
yes,
saying, it's not.
yeah, exactly. Yes,
This made more sense than the other explanation.
yeah.
So can you explain how we see this in the previous way of finding the SSB?
So the previous way of finding SSB overall and then subtracting makes a different point, right? It's not this point. That point was, let's look at all of the explained variance, all of the variance between the groups, and then just subtract because we know they all sum up to the same
But how
thing.
did it do it mathematically? How did it incorporate?
They're very different mathematically. I don't want to try. If you want, we can try to bridge it after the class, but this is not important or interesting to the other people in the class. Okay, so this was the point. Interaction is an actual deviation from additivity. The larger the deviation from additivity, the more convinced we are that there's an actual interaction. A very small deviation from additivity will not be convincing. Now that we found SS interaction, we can look at MS interaction. So these are the degrees of freedom for MS interaction. The degrees of freedom are K1 minus 1 times K2 minus 1. What is K1? The number of groups for variable 1. Number of levels, right? How many levels do we have for the passion? Low passion and high passion. How many levels do we have for the mustache? No mustache and a mustache. So in this case, it's simply 2 minus 1 times 2 minus 1. MS interaction, and then we get F for the interaction. F for the interaction is MS interaction divided by the regular MSW. We find a significant result. Okay. Now, just a second. Sorry, we simply have a lot more to cover, and I don't want to get stuck on this. I'm sorry, I'm stopping you every time. Can you come after class and ask? Okay. Now, what can we conclude? The interaction is significant. What can we conclude? So let's think about the theoretical meaning of an interaction. Now, this is new material now. This is not something you've learned in the recitation exactly. We can conclude two things. We can conclude that the deviation from additivity is larger than 0. Okay? One way of phrasing it, that there is some deviation from additivity. Okay? That's one way of phrasing it. Another way of phrasing it is that the simple effects are really different from one another. They really are different from one another. Okay? So two conclusions we can get at this point. But we also have to check which of the simple effects are significant. This is something we haven't done so far. We only looked descriptively at the simple effects, but we also need to check which of them is significant. Why? Because a simple effect might look like a real simple effect, but can actually occur due to chance. So once we know that the simple effects are different, now we have to ask, okay, which one of them is significant? So, for example, we have this simple effect of passion, right? We have high passion minus low passion in the mustache group. We get 4.2. This is a very large, simple effect of passion, positive effect of passion. But here we have high passion minus low passion is minus 0.2. This is a very small, simple effect. Do you think it's going to be significant? Probably not. Okay. Now, from the descriptive point of view, high passion reduces meaning in life among people without a mustache. But is it really? Right? Can we really trust this simple effect? Probably not. Now, I don't know, right? I have to check. How do I check? I check for significance. Okay. So we can't stop with the descriptive point of view. We have to check it out from the inferential point of view. Is this point clear? I'm feeling like I'm maybe losing something. I need you to nod if it's clear. Okay. No. I knew someone who didn't get it. Okay. It's fine. It's great. Okay. So, I'll go over it again. We have a significant interaction. Okay. But we don't know which one of the simple effects are significant. Why do we care? Because we can have a situation like this. In the no mustache group, it seems like passion reduces meaning in life. Right? We have a negative effect here. But we don't know if we can trust this negative effect. From the descriptive point of view, high passion reduces meaning in life. Okay. But can we really trust that effect? Trusting that effect is something that we have to check by looking at the significance of that effect. Okay, so we can't just stop with the descriptive statistics, we have to go to inferential statistics. Are these descriptive effects real or due to chance? Notice, I'm not going to look at all the simple effects. Okay? We're looking at the effects of passion, once among the mustache, once among the no mustache. Okay? We're not going to look at all the combinations. Okay? This is simply that's how it's done. Okay? You won't see it a lot of times, sometimes you'll see it. But you won't see a lot of times in an article that someone analyzes both these simple effects and these simple effects. Yes?
So how do you know which variable is supposed to be?
The researcher chooses. Right? The researcher chooses which is the more interesting for him or her. It's a theoretical decision, not a statistical decision. Sometimes you'll see both, sometimes, but most of the times you'll see it from one angle, not from the other. Yeah.
When you say choose one variable, you mean one group?
One variable to analyze it from that point of view, right? We're analyzing it from the point of view of passion, right? Because we compare low and high passion. Okay, so how do we analyze simple effects? It's actually rather simple. Not because it's simple effect, it's actually rather simple because it's something that we did before. What we do when we analyze simple effects, we simply focus on one level, right, the mustache level, okay? And we analyze it as if it was a one-way ANOVA. Right? Basically what we're doing is we're breaking down this table to two one-way ANOVAs. And we already know how to calculate one-way ANOVA. So to conduct a simple effect, we focus on one level and conduct a one-way ANOVA. So think about it that the first stop will be this. Okay? I've deleted the no mustache group. Okay? It doesn't exist in my world right now. So I want to ask, what is the effect of passion among people with a mustache? How do I conduct a one-way ANOVA? I know how to conduct a one-way ANOVA. I simply calculate SSB. What's SSB? Variance between the groups. Now, the only difference is that the grand mean that I'm looking at is not the grand mean of all the groups. It's the grand mean of these two groups. What's the grand mean of these two groups? Marginal mean, exactly. So because I deleted the no mustache group, I have only these two groups. And what I'm looking at is the SSB of that simple effect. So SSB A1, okay, it's YA1 because we're only focusing on one effect among one level. It's not really important how you call it. 4.4 minus 6.5. 8.6 minus 6.5. Okay? So I calculate sum of square between the groups only for these two groups. And I get that MSB is this. I have MSB, I need to divide it by MSW. Which MSW? The same MSW. The same MSW that we started with. Okay? Why? We have only two groups. Why the same MSW? Because the MSW that we calculated is the best MSW that we have. Okay? It's the most accurate that we have relative to the population.
But this is a different population now because so many mustache people.
If you want, I'll throw you a sentence, and if you want, we can discuss the philosophy behind it afterwards. It's because we assume equal variances that this is our best MSW. Because we assume that basically the variance here and here and here and here are the same, the more people we have, the better the MSW. Not the better for us, the more accurate the MSW. So what did we do? Okay, we found a significant interaction. Now we're looking at the simple effects. We're focusing on one level of the mustache groups, right? And then we simply analyze what's the between group variance of these two groups. And from there, it's the same process that we already did tens of times before. Okay, SSB goes to MSB, MSB divided by MSW, and we find a significant simple effect. What can we conclude? We conclude that the effect of passion among people with a mustache is a real effect. We can rely on it. Nietzsche can write in his next book, people with a mustache and high passion are have more meaning in life than people without a mustache. Than people with low passion. Now I'm going to return to this. Okay. Oops. Like this. Now we can ask, what is the effect of passion among people without a mustache, right? The other simple effect. So now we're just focusing on these two. SSB is this minus the grand mean, and this minus the grand mean equals this. MSB, not surprisingly, is very small. And we get that F is very, very, very small. So we cannot conclude that this is a real effect. Okay, so from the descriptive point of view, high passion increases meaning in life for people with a mustache, but decreases meaning in life for people without a mustache. From the inferential point of view, high passion increases meaning in life among people with a mustache, but does not affect the meaning in life for people without a mustache. The descriptive effect was not significant. Okay, questions? Yes.
Why didn't the degrees of freedom change?
The degrees of freedom for the MSW or the MSB?
Oh, because we're using the same.
Same MSW.
So we use the same degrees of freedom. We use the same level.
No, but like.
Same MSW, absolutely.
But we divide
Well,
it
there's less
into
people.
two. We have now the 4 groups instead of 2.
Yes, but we use the same MSW from the overall ANOVA. That's why the degrees of freedom remain the same for the MSW, right? What's this 16, right? Degrees of freedom within. What's degrees of freedom within? And degrees of freedom for the MSW. Same MSW, so same degrees of freedom. I'm going to give you a more extreme example of this. This is the conclusion from this slide. Our interpretation of the interaction can change when we actually analyze it. The interpretation from the descriptive point of view can be different from the interpretation from the inferential point of view. So, for example, in this case, yes. Previous to this?
Yeah, okay, so the reason for in between, is
Yeah.
there one because you're using 2 variables or
2 levels. Yeah.
So if there's another level of 2.
Exactly. If we have low passion, medium passion, and high passion, we're going to conduct a one-way ANOVA for 3 groups. Right? This is exactly one-way ANOVA. So let's look at a more extreme example. Okay? Now, so let's say A and B, okay, and we have 2 simple effects, okay, and we have this blue line is real, okay, is a significant simple effect, but this black line is not significant. Okay. So let's analyze it together. Let's look at the effect of B among A1. Effect of B, B2 minus B1, among A1. So we get 8 minus 5 equals 3. Okay, that's one simple effect. Let's look at the other simple effect. 4 minus 3 equals 1. Now these simple effects, do they have the same direction? Yes, right? Both are positive. So from a descriptive point of view, this is an ordinal interaction for variable b. Okay? From a descriptive point of view, this is an ordinal interaction. We can trust the effect, the main effect of b, because the simple effect is the same, right? Same direction. But now I'm telling you that there is no real effect of b among A2. If there is no real effect, we consider this effect to be 0. If the effect is 0, how would you call an interaction where one of the simple effect is there but the other is not? You'll call it a disordinal interaction. So from a descriptive point of view, this is an ordinal interaction. From an inferential point of view, this is a disordinal interaction. So this tells you why it's important to analyze the simple effects. Okay, let's replace the A and B with actual values. Let's say it's Ritalin, okay, what we said before. Ritalin among ADHD and Ritalin among no ADHD. Okay. If you look at it descriptively, it seems like Ritalin affects everyone, right? And everyone should take Ritalin. Okay? And you're the doctor and you look at it from a descriptive point of view. Of course, you should take Ritalin and you should take Ritalin and everyone should take Ritalin. But then you look at the inferential statistics and say, oh, I can't really trust this effect. This effect is not really significant. So I can't really conclude that Ritalin affects people without ADHD. So now, when people ask me, hey, doctor, should I take Ritalin? Wait. It depends. Do you have ADHD or you do not have ADHD? Okay. So from a descriptive point of view, everyone should take Ritalin. From an inferential point of view, no. Only people with ADHD should take Ritalin. I told you that this is significant and this is not significant. We didn't really analyze it. Given. So again, it exemplifies the point. It's not enough to look at descriptive effects. You have to analyze the interaction completely until the bitter end, until you understand it completely. Okay, we have, I think, one more slide. How are you? You're not bringing chocolate to class. I told you should bring chocolate to class. I'm bringing chocolate to class and I'm teaching it, so of course you have. I'm running around, I have adrenaline. You're just sitting in there and just shutting down moment to moment. This is complicated. Again, this is something you have to analyze with the TAs. What will happen in this situation? Okay. So, there is a significant interaction. This simple effect is significant. This simple effect is not significant. Now we know that B1, B2, and B3 are different among A2. Which one of them is different? Right? It's an open question. They're not all necessarily different from one another. What's the solution? Whenever we have three levels, whenever we don't know what's the source of the significant effect, we have to do what? Post-hoc.
Why aren't they all different?
So we say that there is a significant effect among three groups. We say there is some difference between them, right? It's not a conclusive answer. We want to know what exactly is the difference.
If we were talking like descriptively, we can say there is a difference between each one.
Yes, but inferentially, exactly. So for example, this might not be significant. This we can only see if we look at post hoc tests for the different levels. Is there a difference between B1 and B2 among A1? Is there a difference between B1 and B3 among A1? Is there a difference between B2 and B3 among A1? And so on and so on. Now this is, you're going to go over it with the TAs, you're going to know how to analyze it. It's going to be a very long and laborious process. Now I'm going to assure you that you're not going to have to do all of it in the test. It's not going to be from bottom to top, okay? We might ask you to do only this last step, okay? Only one step. This will show us that you know how to do it. And again, this we'll do with the TAs, not in the class. For the follow-up comparisons, okay? We follow up on anything that we don't understand. The general rule, whenever we don't fully understand the effect, we have to follow up. So if we have a significant interaction, we always do a simple effects analysis. We analyze one simple effect, we analyze the other simple effect. If the effect is significant and has more than 3 levels, right? One simple effect is significant and has more than 3 levels, we post hoc the simple effect. If the simple effect has only 2 levels, for example, like we had here, okay? If this effect is significant, there's no reason to do a post hoc, okay? There is no question about it. The 2 groups are different, right? Post hoc you only do if you have more than 2 groups. So significant with 2 levels, you stop. Non-significant, you stop. Okay? If you have a main effect, if it's significant and has 3 or more levels, post hoc, significant with 2 levels, you stop. Non-significant, you stop. Okay, so next week, quiz about the two-way ANOVA. I'm going to try to be light on you as I promised. Can't promise too much, but I'm going to try. All the videos are online. I can see the YouTube count of how many views. Not a lot of you are viewing my videos. I'm starting to think that maybe it wasn't that a great idea to take all this effort. I know you're going to use them before the test.
Yeah.
But use them, okay? Go over them. Look at the presentations if you have the time, okay? Everything you already know. It is very, very simple, only a bit confusing. Try to understand how to overcome the confusion. Okay, thank you very much for participating and listening, and see you next week.